So my final lecture in this, this sequence, I want to go into talking about the science that we're getting out of these detections, both the, sort of from the standpoint of foundational physics, studies of gravity, and the astronomy and astrophysics that we are doing with them. And I'm also, towards the end, I'm going to talk a little bit about some of the things we expect in the future, especially some of the measurements that people are planning to do with LISA. And I'm going to talk a little bit more about some of those extreme mass ratio sources that I described briefly in my public lecture last night. Okay, so let's move forward here. So fundamentally, when we measure a gravitational wave, what are we measuring? So generically, what you're measuring is some kind of a sinusoid. Okay, so you measure an amplitude and you measure a phase. You measure that at a particular signal-to-noise ratio. Okay, and so you always have to bear in mind that you're measuring these things with some uncertainty. The amplitude is typically measured with a fractional error that is roughly 1 over the signal-to-noise ratio. The phase is measured much more accurately. It tends to be measured with a fractional accuracy that is also 1 over the signal-to-noise ratio, but also then divided by the number of cycles in your measurement. So what this means is that as you're thinking about the different characteristics of your system and how they influence the waveform that you're trying to measure, things which influence the phase tend to be measured a lot more accurately than things that influence the amplitude. So let's talk about this in the context of some of the waveforms that I went through and described yesterday. So let me just use as my initial example, I went through yesterday and I developed the gravitational waveform that you get if you assume Newtonian gravity and Keplerian orbits, and you couple that to the quadrupole formula to give you the gravitational waveform and the phase evolution of that gravitational waveform. So here are my two polarizations. So there's a particular amplitude function, the two polarizations that are related to sort of the inclination angle that that system has with respect to your line of sight. And then they are then given by an integral. The phase of these things is given by integrating up this frequency as a function of time, which we derived in yesterday's lectures. So if you can measure the phase, notice that this phase function, the only intrinsic characteristics of the binary that enters into this phase function is this combination of masses called the chirp mass. So if you measure the phase accurately, you've measured the chirp mass accurately. If you can measure both amplitudes, the amplitude of both polarizations, you can get information about this inclination angle that describes how this thing is tilted with respect to your line of sight. If you can do both of those things, so notice that this chirp mass also enters the amplitude of both polarizations. So if you measure the phase, get the chirp mass, measure the amplitudes, and get this inclination parameter, the only remaining free parameter that comes out of this thing is the distance. So measure the phase, measure both of your amplitudes, and you have characterized an enormous amount of information about this system. Now, the real waveform, this waveform is, of course, I'm doing a very approximate thing here. I'm treating gravity as being just that Newton wrote down, and the quadrupole formula for gravitational waves. I showed you guys some examples of you remember I wrote down what the acceleration is when I include sort of those post-Newtonian corrections. We ended up with equations that sort of vomited all over all over the screen here. When you include all those different effects, you focus yourself down on simple circular orbits, what happens is that there are then higher order corrections to how the frequency evolves. And those additional corrections, they don't just depend on the chirp mass, which is entering here. You also find that they depend on the mass ratio of the system in a different way. You find that they depend on certain parameters that encode information about the spins of the members of the binary and how those spins overlap with the orbit of the system. So as we include more information about strong field general relativity, additional information about the characteristics of the system are imprinted on this waveform. And you guys now heard me twice play the little audio encoding of coalescing binaries. And when I played the one that was the signal that you get from two rapidly spinning binaries, you may recall that the waveform itself, the phase, it wasn't just the amplitude had these wiggles, but the phase had that sort of characteristic to it. And the reason for that was that the frequency evolution itself depended upon. So if you imagine that the spins are precessing and the orbit is precessing, these terms, sigma and beta, which are related to the spins in the angular momentum of the system, they are going to oscillate. That means that the frequency evolution has an oscillation on top of it. So this is the way in which all this additional strong field structure gets imprinted on this thing. Makes the signal a lot more complicated. But it also puts a lot more information that we hope to get out of these things. You know, if you learn about the masses, you learn about the spins. If you can measure the phase accurately, you can measure the masses and the spins accurately. So in this model I put together here, I'm sort of only considering the case of the wave of the bodies as they're sort of widely separated and they're slowly coming together. A more complete model, which allows us to build, for instance, to do the analysis of this is the discovery event here. Let's think about what goes into this. So the early cycles of this thing, those correspond to what I just went through on the previous slides. These are the binaries, or the binary when its members are widely separated and they're slowly coming together. As I approach this peak here, the middle region corresponds to when they sort of hit a general relativistic instability and they plunge and merge, form a single body. And then at last, you get your final cycles here that encode the ringing of the remnant that's left behind by the coalescence. So when one is actually doing these kind of analyses, I described to you in my last lecture how you use information about the detector noise and the general relativistic model to make the filters, the templates that are used for these analyses. Badri showed in his talk examples of the filter banks, the template banks that are actually used for the analyses. This is what goes into all of these things. It's a full model that describes how you go from widely separated to essentially a single black hole ringing down, at least when we're talking about some of these binaries. So let me just go through a couple of the examples here. Badri has done a little bit of this as well, but I sort of want to put my own spin on a few of the details of this thing here. So when we looked at GW, the first discovery event, GW 1509-14, there's on the order of 7 or 8 or so cycles here before it comes in, coalesces, and then sort of it rings down. There's enough here. Badri did this really entertaining exercise yesterday where you plot frequency to the -8th power as a function of time. And from that, the slope of that law immediately encodes what the chirp mass is. And that's a simple way to get that. Now you do the analysis with a fuller model, and that's what allows you to get it with this relatively tight error bar. When you then include information that comes from this full model, which builds in these effects having to do with the total mass of the system, the mass ratio of the system, the spins that can influence it, that's what allows us to say that the individual masses that made this work must have been 36 and 29, modulo some error bars, and told us that the final mass was 62. Now, when we went through all this, let me just go back. I'd like to write a few things down on the blackboards here. So let me go back to, this one here. So my H measure, I have an F plus that depends on all these various angles, and an H plus that depends on I and distance. So I'm going to ignore chirp mass for just a moment. Let's assume chirp mass is measured perfectly. Go back forward to this. Okay, so this guy again. So the sky position of this event was determined to about 600 square degrees. If anyone does any astronomy, you know that that is terrible. Okay, the full moon, set to scale, is 1/4 of a square degree. So this is equivalent to an area of about 2,500 full moons. Okay, and if you're trying to locate on the sky an event that may be short-lived, that's a tall order. Okay, you're really not going to be able to do that very well. So, but why is it that it was determined so badly? Well, when I say the sky position is determined to this thing, that's basically saying that the errors in theta and the errors in phi were sufficiently bad that a single detector measures this combination of these things, and it doesn't allow me to separate out what is H plus and what is H cross. So I'm just measuring some linear combination of all of these functions, okay? And so I don't have enough information from a single detector to distinguish what is the plus polarization from the cross polarization, which doesn't allow me then to break out the angles theta and phi with very much accuracy. So then you say, aha, but LIGO has 2 detectors. The problem is that the 2 LIGO detectors are designed so that their arms are nearly parallel to one another. And so what that means is that F plus and F cross for the 2 LIGO detectors are almost identical. Now that we are in the era of common detections, many of us sort of look at that and go, what the hell were you thinking, right? And it would be so easy to correct that. If one of those detectors were rotated by 45 degrees, it would actually pick up the orthogonal combination of those 2 polarizations. But remember, when this was originally funded and originally put together, and to be perfectly blunt, given how strong the first detection was, I fully agree with this decision. No one knew how common these events were going to be. And so the decision was, let's design this so that we have unambiguous first discovery statistics. And the way to do that is to make sure that the 2 detectors basically see the exact same signal. Okay? And that was, now it's a little bit annoying. I used to joke that after the first discovery, what they ought to do is, Hanford's in the desert, sort of the middle of nowhere. If it were on a giant turntable and they could just rotate those arms by 45 degrees, that would be great. LIGO management doesn't like that suggestion, but there you go. So because of this, when it was just the 2 LIGO detectors, you really don't determine the sky position very well. And so as a consequence of that, since the sky position is not determined very well, you don't really know whether the system is face on. You also can't determine what the inclination angle is here. So let me write down one other formula. So H plus is proportional to 1 plus cosine squared of that inclination angle over 2 distance. Not 2, over distance. No, there's a 2, that's right. And the other one is proportional to cosine of that inclination angle divided by the distance. So since we don't actually know how much of these signals is H plus or H cross, it could vary from being all just H plus to equally divided between H plus and H cross. And what that means is that the ability to separate out 1 plus cosine squared and cosine from the D is uncertain by about a factor of 2. And indeed, when you look at what the range of the allowed distances is, this goes from the minimum allowed distance, 410 minus 180, to 410 plus 160. It's roughly a factor of almost 2. So that's why these initial events, when they were discovered, relatively poor sky position determination and errors in the distance that are uncertain like that. The second event that was detected, so what's interesting about this one, so remember, this one's about 8 cycles of binary coalescence. The next one that was announced was 15, 12, 26, much longer in-spiral, so close to 60 cycles in that in-spiral. And remember, the in-spiral is really governed by that chirp mass. Look at the errors on the chirp mass by consequence. Okay, this thing, it's a smaller number, but the error bars are much tighter. It's simply correlated with the fact that instead of measuring 8 or so cycles, you're measuring over 50 cycles. Immediately cuts down on the errors associated with this. It turns out that the error bars on the final mass are a little bit larger. Okay? Again, because up here, all this signal is that sort of loss in the noise. It's not determined as accurately. This is another one where the errors in distance are spookily similar to the way they were with the first one. And it's again because you just have these 2 detectors. You have this degeneracy between distance and inclination angle. There's just nothing you can do about that. And the sky position is about a factor of 2.5 worse, basically because it's not quite as strong. Okay? Amplitude, the sky position comes from measuring the amplitude of these signals. The amplitude was lower. The sky position was determined more poorly. So what changed with this one? So this was one where you can see there's, again, only about 10 cycles. Many of the source parameters are very similar to what we saw for that initial discovery event. But the sky position was determined to an order of magnitude better. The difference was Virgo contributed to the discovery. Throwing in a third detector, which is not sort of in this parallel to the others design, immediately breaks a lot of degeneracies among parameters. and sharply fixes things up. Now, it's still the case that the distance determination is actually somewhat better. It's not hugely better, because at the end of the day, it was still a relatively, it was pretty strong, but there's not a lot to go on here. But that gets better and better as time goes on. So what we've learned from these so far, I mentioned this in my public lecture last night. So all the earlier, prior to the gravitational wave discoveries, this is a significantly out-of-date figure, but it's still kind of nice for illustrating this. These ones down here in purple, which I'm afraid are a little hard to see, these are all the black holes that had been known largely from studies with X-ray telescopes of things that are in high-mass X-ray binaries for the most part. And so those were the stellar mass black holes that were the most accurately characterized prior to the first gravitational wave direct detections. And it was sort of on the basis of our knowledge of these things that the expectation was that we may get an occasional rare event involving things that have 10 solar mass black holes in them. And so we got the first event, which involved two black holes that were nearly 30 solar masses colliding and producing something of more than 60 solar masses. And people kind of went, to paraphrase a famous quote from physics, who ordered that? It really was quite a surprise. There was no astronomical expectation prior to this. In the way of good astrophysicists and good model builders everywhere, within a week of this event being published, there were dozens of papers publishing models that explained exactly how to make black holes like this. And actually, that's not quite accurate. In the week before the announcement, while the rumors were swirling, there were dozens of papers being published purporting to explain how you could make these, which was very entertaining. Speaking for myself, let's get a little bit more personal now. One of the things I'm most interested in seeing as we continue to make more discoveries is learning about the spins that we get in these binaries when they're widely separated from one another. So in my second lecture, I described the way in which when spins in orbit are misaligned, you get these strong modulations, which encodes information about the geometry of the binary as it approaches coalescence. This will actually be very difficult to measure with these gravitational wave sources that we are currently seeing. The reason is that that modulation is imprinted on the relatively low frequency part of the waveform. And given how massive many of the sources that we are seeing are, that is going to be in a region of the detectors where the sensitivity is just not as good. Okay? So we're going to be pushing down the low frequency sensitivity, but we need to sort of think other ways to try to get some of this information out. Now, why is this so interesting? How the spins and the orbits align with one another is it will certainly vary substantially depending on the binary's formation history. So the expectation is that if you have a pair of, and this is I should give credit, this is Carl Rodriguez, who is a postdoc, done some work with me. He was at MIT. He's actually moving to a faculty position in Pittsburgh pretty soon. He produced this video. He's someone who studies the formation of binary black hole systems. So imagine I have a binary star system, and the members of this binary, these two stars evolve and produce black holes and form a binary black hole. So the first star in this binary goes supernova, leaves behind a black hole. Now, the other one is slightly less massive, so it doesn't evolve quite as quickly. So a few million years later, this enters a giant phase. Giant stars are very low density, they're very soft and easily deformed, and so what happens is it becomes totally distorted, and the system enters a common envelope phase, where the black hole that formed first in this binary is now inside the envelope of its companion. Basically, due to viscous drag, it will be dragged down and then sort of deep within almost the atmosphere of this star, the black hole will orbit the core of the second star, till eventually the envelope is unbound from the system, the core produces a black hole, and you wind up with a pair of black holes orbiting each other. Now, if these guys are spinning, you expect in this situation that their spins will be fairly close to parallel with one another and aligned with the orbit of the system. The actual value of these things, pretty hotly debated how rapidly spinning they would be. I have to mention there was a paper on the archive this morning claiming that in this scenario, you actually expect the spins of these things to be close to zero. I mean, this is, it's yet another model, so take it with a grain of salt, but it's a testable hypothesis. Imagine that these two stars are not actually in orbit with each other. They're two stars sort of in the field of a cluster of stars. Okay, so one of them forms a black hole. It's not orbiting this other guy, so that guy becomes a giant, does not go inside the common envelope, and not close enough, so it eventually disrupts, forms a black hole. But what I didn't tell you is that these two black holes are themselves close to one another and in a field with lots of other stars and compact objects. You can have a third body, so ordinarily they would pass close to one another. They would just do what Newtonian gravity would call a hyperbolic orbit. They'd have a brief encounter and then they go on their merry way. But if there's a third body that comes along, they can exchange energy and angular momentum with that third body. And if it's in something like a globular cluster, this will happen all the time. You can then eject this third body and leave these guys in a bound orbit with each other. And because of the random nature of this encounter, the spins of the black holes and the orientation of the orbit have nothing to do with each other. It's going to be completely random in that case. And so this is the dynamical formation mechanism that this is something that Carl particularly studies. He's got, it's a little hard to see, but he has a little video. Yeah, you can sort of see there's lots of little black holes and stars dancing around here. I'll try to send a link to this, posted along with this thing. You can go to Carl's webpage and see movies of binary black holes forming in the cores of globular clusters. So that's one of the reasons why we're so interested in understanding all the characteristics of these things. You know, it's not just about building catalogs of masses and spins, even though, having had no data for much of my career, being in a state where I have catalogs of masses and spins is kind of cool in its own right. But it's what you can do with them. It's the fact that this really gives you a tracer to sort of the astronomical archaeology of these objects. Now, let me switch gears a little bit. Everything that I have described in my lectures so far, and this gets to a question that I was asked a little bit earlier, assumes that general relativity completely describes the physics of gravitational wave sources. General relativity has passed every test that we have thrown at it, but that doesn't mean we stop testing. So what we can imagine doing is, again, bearing in mind the fact that the phase is something that we can measure with very high precision. We can ask ourselves, how would this change if let me go back a little bit. How would this change if I assume some kind of a modification to Einstein's standard theory of general relativity? I'm going to just briefly go over this because the truth is this is a very deep subject. It's something that we could spend multiple lectures on going through in detail. But the essential answer boils down to, it depends on how you choose to modify things. I'm going to give you two examples here. So let's imagine that the graviton has a mass associated with it. Let's imagine there's a graviton. So if I assume that these two things are true and it has a mass, well, it would turn out that the group velocity associated with gravitational waves is highly sensitive to what that mass actually is. And so it'll change the frequency evolution versus the general relativity prediction. So, there's no necessarily reason you might sort of suspect this, but it's a testable hypothesis. You go out there and look at it. This has actually been done for years by people studying what you can kind of think of as the Coulomb potential of a mass. Okay, sort of the normal 1/r Newtonian potential of a mass. If the graviton were massive, it would go over to more of a Yukawa form, where it would be e to the minus graviton mass over r divided by r, and it would fall off much faster as you go to large radius. But it turns out if you have dynamical gravity, you get these very interesting propagation effects that happen. What happens with this is that high frequencies travel faster than low frequencies. Now, ordinarily, when you see an n-spiral, you get the low frequencies first, middle frequencies, and at the end of the n-spiral, you get the high frequencies. This would make those high frequencies actually begin to catch up, and the entire waveform would sort of get squashed and change its shape. And so you can use the various waveform catalogs that Badri and I have shown you that have been detected so far and say, okay, let's throw this in here. Given that it matches general relativity so well, let's turn that into a bound on what the mass of the graviton could be. And it turns out it's best described by converting it to a Compton wavelength. If it does have a mass, then the Compton wavelength associated with that mass is greater than 10 to the 13 kilometers, which is pretty big. Another thing that people can do, general relativity is perhaps most naturally thought of from sort of a foundational physics point of view as arising from the Einstein-Hilbert action. If I write down this action principle, subject it to a variation, something like the Palatini variation or something like that, the GR field equations follow this. Okay, but why do this? Perhaps this is just the lowest order term of a sequence that involves all kinds of higher order corrections to this thing. Possible. And so a nice paper by Vito Cardozo sort of putting this out here. And this becomes a way that we can begin to study how higher order corrections to the gravitational action would change gravitational wave emission. What you find, look at this paper to get various details. You change essentially the orbital properties somewhat. It changes gravitational wave propagation. This is an example of one of the ones that would give you additional polarization states. With some of these, so a term that looks like this, what's fascinating is this introduces a handedness to gravity. And so you find that you can, I've described these two polarization states. Depending on what their phases are, you can make a combination of them that becomes circularly polarized. If you have an action like this describing your fundamental gravity theory, you find that clockwise polarized gravitational waves propagate at a different speed from counterclockwise propagating gravitational waves. So if this were the case, again, I would say this is just, it's something that you test. And so people are digging in on this right now. I've talked a little bit about ring down. So if the coalescence is a spinning Kerr black hole, the final waves are sort of going to be modes of that spacetime. I described you sort of heuristically the way in which when you deform a black hole, it's got these damped sinusoids that describe how the late time waveform essentially drives the spacetime down to the solution that Roy Kerr wrote down, which describes a rotating black hole. Now, for a Kerr solution, every one of these frequencies and damping times is set by the mass and the spin of the final black hole. That again becomes a testable hypothesis. If you can measure multiple modes of this thing, you then wind up with a consistency check. If this spacetime is only governed by the mass and spin of the final black hole, you have, let's say if you measure just two of these modes, well, that gives you enough information to get the mass and the spin. If you can measure three, that third one overdetermines the system. You had better get a result that's consistent with the first two if Roy Kerr was right. If you discover a deviation from that, okay, actually the first thing you do is you assume you made a mistake and you go back in and you do a systematic analysis of your data. But if you consistently find that there's a disagreement here, you've discovered that the Kerr solution has structure beyond what the no-Hare theorem demands. And again, so more work about this. I'll refer you to a paper that discusses how that can be done in practice. One thing which I have to highlight a little bit of work that my own group has done, even if you don't, let's say, suppose you trust Einstein, who's pretty smart, and you sort of think to yourself, probably the no-Hare theorem is fine. If you can measure multiple modes, that actually gives you information about the binary that produced these waves. So I'm showing you a figure here from a paper that was written by some members of my group and I, where we're comparing, so we have a rotating black hole, and we're comparing what happens if this is excited by an object that merges with this thing on a trajectory that lies in the equatorial plane of that black hole versus the trajectory that is highly misaligned from the equatorial plane of that black hole. And what you find is that when they are aligned, almost all of the power comes off in the L equals 2, M equals 2 mode. There's a little bit in L equals 2, M equals 1, and then there's practically 0 in all the others. If it's highly misaligned, then you actually get a much more even spread of power among all the different modes. So perhaps not, even if you're not interested in a gravity test, this may be another way to get at some of the astrophysical information about whether orbits and spins are aligned with one another or not. The things that we were able to do with the binary neutron star, sort of, where to start. This was an amazing event, largely because of these roughly 2,000 or so cycles that this thing spent in band. So this was, a signal that actually, you can get audio encodings of what this thing looks like, and they're really pretty damn boring because it just kind of goes for over a minute. But that means that in terms of the science we can do with it, it's glorious. So because you have so many cycles in band, your ability to determine the parameters that affect the phase is exquisite. Look at the error bars associated with the chirp mass was measured on this thing. Okay, so this thing is measured with sub-percent level precision, the chirp mass of this object. You also get the distance to much better accuracy than you do with any of these others, and this is one where the sky position was nailed down quite accurately. This was in part because, so it's something which I believe Badri mentioned as well. It just happens to lie. So this was a signal that was strong enough that Virgo should have seen it with a signal-to-noise ratio. It was in a factor of 5 or so of what the LIGO detectors would have detected it at. They saw nothing. The fact that they saw nothing was actually very interesting information, because I told you it was probably, so these antenna response functions have nulls. There are certain directions to which they have 0 sensitivity. They're relatively small, but if you happen to be in them, you're not going to measure a signal. Virgo didn't get one, so they said, must be in one of the nulls of this detector. And indeed, there it was when they pointed telescopes at those locations in the sky, folding in addition, information from the 2 LIGO detectors. That's how they were able to find the object that hosted it. So one thing which I would like to spend a few moments talking about is this wonderfully measured distance. Now, distance is one of the hardest things to measure in astronomy. Typically, when you are doing astronomy, you look at the sky and you see little spots of light. Okay, so how do you get distance from this? So if you're trying to make measurements within our galaxy, there's a lot of techniques you can use, often based on parallax. You can use the fact if you're looking at a signal at a source now, you look at it 6 months later, the Earth is on the other side of the sun, and the relative position of that source compared to background objects will have apparently shifted. And you can use the degree of apparent shift to determine how far away it is. If you want to go beyond our galaxy, though, that doesn't work. Objects are just too far away. That apparent positional shift is too small to measure. And so what is typically used when you go beyond our galaxy is an object called a standard candle. The basic idea is that you look for some kind of an astronomical source that you understand so well you are confident you know its intrinsic luminosity. Set aside for a moment how you get that object. Let's just imagine that nature has provided us with giant light bulbs, and they've got the brightness of those light bulbs written on their sides. So if I have 2 such light bulbs and I look at them through telescopes, this one's going to be 4 times brighter than this one. Problem is that situation I set up for you was absurd. Nature does not provide us with such light bulbs. We have to come up with objects and we have to calibrate what their intrinsic brightness actually is. So one of the best examples of this was something that was discovered by Henrietta Swan-Leavitt when she was studying variable stars in the Large Magellanic Cloud. So the first approximation, all objects in the Large Magellanic Cloud are the same distance away from us, okay? You know, they vary by a little bit, but it's about 100 kiloparsecs away, 50 kiloparsecs away. So they're sufficiently far away that the little scatter is irrelevant. And what Leavitt found was that these bright stars, these bright variable stars, had a period of oscillation whose period correlated directly with their luminosity. So the brighter the object was, the longer the oscillation period. And so by calibrating this with a population whose distance was known, they were able to say, if I can find the same stars in distant galaxies, I'll assume that the physics in the Large Magellanic Cloud is the same as the physics in, say, the Andromeda Galaxy. Seems like a reasonable hypothesis. Then, you know, when I find stars whose period, I don't know what this is a log base of, let's say it's days and it's base 10. So these will be ones that have a period of 10-day oscillation, and this WI index essentially tells me about their intrinsic luminosity. This one has a period of 1 day, and I can see that the brightness is a little bit different. And so by calibrating to this population, looking for them in other galaxies, I can infer distance. The problem is, even though this is a very good standard candle, you need a precise characterization in order to set the absolute scale associated with them. And so what I like to say is this is not really a standard candle. It's more like a standardizable candle. And it's only as good as how well you can standardize it. The way that this is done with Cepheid variables is we see Cepheid variables in our galaxy. Some of them are close enough that we can measure their distance using parallax. So we measure the distance with parallax, we study that object, we do a population of them, we calibrate them in our galaxy, we take them out a little bit further. There's another set of standard candles that work at larger distances, in particular type 1a supernovae. They tend to explode with a luminosity that is, to first approximation, the same at every event. It's a little bit of scatter, but that can be corrected for. And so modulo the calibration, if you see a type 1a supernova go off, its luminosity tells you how far away it is. Well, let's turn now to this binary neutron star that we talked about. So as I said, this is one where we got these final 2,000 cycles. We got this distance that was measured from this thing. And we also know the galaxy that hosts this object. From the counterpart, we were able to measure the angles with high precision. So we got these angles that are nailed down. And so we ended up getting very good constraints on both the source distance and on this inclination parameter. What you can do then is say, you know what, I'm going to use gravitational waves as my way of measuring the distance. And then I can use the optical object that I've picked this thing up to learn about the intrinsic characteristics of this thing and use gravitational waves as a new method for determining the distance to astronomical objects. This was an idea that was first developed by Bernard Schutz, published in a paper in Nature now 33 years ago. And then this is one of the pieces of work that is probably one of my more important things I did with my colleague Dan Holtz, was helping to further refine some of these ideas and showing what can be done if you connect it to an electromagnetic counterpart associated with this thing. So these objects have now turned into a new standard for determining distances in astronomy. In particular, if you can associate the coalescence with gravitational waves and photons, you simultaneously determine the source's distance and its cosmological redshift. So if the object is relatively close by, then its cosmological redshift is directly proportional to its distance. And the constant of proportionality is the Hubble constant. What's fun is that right now, the standard techniques that people usually use to measure this thing disagree on what the Hubble constant's value is. So there's a set of values that are based on using standard candles, largely Cepheid variables and type 1a supernovae. They are based on objects that are measured out to about a redshift of 1. So in other words, out to several thousand gigaparsecs away. And in the units, so this is kilometers per second per megaparsec, it's not that important, they get a Hubble constant whose value is a little more than 73. You can also do this by measuring the properties of the cosmic microwave background. Okay? It's a very different kind of technique, and I want to get into the details, but it's very well developed. And they get something that is systematically smaller. Now, when this difference first showed up, a lot of us kind of looked at that and went, huh, that's interesting. But the error bars were a lot bigger. And so the assumption was, as the measurements were refined and the error bars were made bigger, it was sort of assumed that the two values would come closer and closer to each other. The exact opposite has happened. As the measurements have gotten better, indeed the error bars have gotten smaller, but the peaks of the two distributions have actually begun to move apart. So this is actually a pretty big mystery in cosmology right now. Have we overlooked some kind of a systematic effect that is actually biasing either this one, or both? Perhaps there's actually physics that we have gotten wrong. Okay? Maybe there is some additional contribution to the energy scale of the universe on large scales that we don't know about. You know, maybe there's some kind of a sterile neutrino or something like that, very low mass object that sort of has a contribution to the Friedmann equation that scales with redshift in a way that's different from all the other different species is going in there. Or perhaps general relativity is failing on the largest scales. We really don't know what this is. One of the things that some of us have proposed is that by using this technique, especially if we can do this over a range of measurements, perhaps this will give us enough precision to begin to discriminate among these different possibilities. Now, using the binary neutron star, we've got one data point. And unfortunately, it lies right between the two competing values. Now, don't take that too seriously, because with that single data point, we also don't really have precision to sort of say one way or the other. The truth is, both of them are perfectly compatible with this. I would just take this as a proof of principle that this technique can be used. Paper that some colleagues and I put together showed that if you are able to repeat the binary neutron star measurement somewhere around 10 to 30 times, we should be able to get enough statistics that we can at least distinguish one hypothesis from the other. My personal feeling is that it's very likely with the things that we're measuring with binary neutron stars, if we can do this, I think we're going to wind up being closer to the standard candle value, because it just seems to me that all of the techniques that measure Hubble at low redshift get a fairly high value. All the ones that measure it at high redshift seem to be getting a bit of a low value. I don't know whether that's systematics or it's new physics, but data will tell us. If we can go to larger distances, we may be able to do more than this. We may be able to do these things at different redshift. And indeed, the future ground-based detectors may do stuff with this as well. So this is an exciting direction for the future.
So we need like more than 50 or 100 events to actually narrow things down.
So in this analysis that we did with Samaya a number of years ago, I forget some of the details, but our claim was that more like 20 is already enough to begin discriminating at least between these, okay? So take that with a bit of a grain of salt. It's been a number of years. So what's funny is, here's a small anecdote and rant. You can find this paper on the archive, okay? But you cannot find it published in the journal. It was rejected. And the reason is that our referee report told us that it was an interesting analysis, but it was highly unlikely that we would detect binary neutron stars. We would detect an electromagnetic association with binary neutron stars. And then those of us who were writing it got busy with various things, didn't have time to get a rebuttal together sort of in time. And in the meantime, while we were sort of contemplating doing that, GW 170817 was discovered. I actually almost want to just send it back with like a Post-it note attached to the referee report and say, what do you say now? At any rate, rant. So I want to wrap up this discussion with talking a little bit about one of my personal sort of loves in this field, which are these extreme mass ratio events that I alluded to and did a little bit of discussion of in my public lecture last night. So this is a source for the LISA detector, where the basic idea is you're trying to find sort of a small 10 to 100 solar mass black hole on a strong field orbit of a 1,000,000 solar mass black hole. So essentially, think of that same dynamics that was in that little video I played for you at the beginning, the stuff that my postdoc Carl put together, of the dynamics in a globular cluster. But now imagine that it's actually in the star cluster at the center of a galaxy, and in the center of that star cluster, there's a 1,000,000 solar mass black hole. So roughly every 100,000 years per galaxy, the many-body interactions, I talked about this a little bit off on the side in my lecture last night, there will be strong dynamical interactions between black holes in this core that will put one of them onto a strong field orbit of that big black hole. When that happens, we wind up with a binary that has fascinating properties. So first of all, when we think about this from the standpoint of general relativity, it'll be a system that has a very large mass ratio. So I will have a 1,000,000 solar mass black hole, for which, if general relativity is correct, we have an exact solution, the Kerr metric of general relativity. And it's then being perturbed by the relatively small effect of a black hole that is much smaller than it. So I know how that this guy solves the Einstein field equations exactly. If I then take and I require that this sum satisfy the Einstein field equations, this allows me to develop a set of equations that govern this perturbation, and I can study that perturbation and figure out how this thing back reacts on the system and how this binary then evolves. One of the more important papers laying the foundations of this was actually written by Professor Aliyev's PhD supervisor, Dmitry Gotlov. And so many of these things, there's a long history to doing this work. This paper was published in the 1980s, I believe. Yeah. So this is something that there is a very active subfield of people who are working on. And I have to highlight that we have begun, there's a tremendous number of people who have just sort of reinvented the wheel, sometimes 19 or so times. And so some of us have decided people need to stop doing that. We have some really good tools. And so we are now putting out a set of open source tools that can be used to do this if you want to study black hole perturbation theory and many properties of black holes and orbits, the properties of bodies orbiting black holes. So let me tell you a little bit about some of what goes into this. When you have a system whose mass ratio is that strong, that extreme, to 0th approximation, the small body is just moving on a vanilla geodesic orbit of that black hole. You can look up the properties of that orbit in any of the more, you need to get a somewhat more advanced general relativity textbook, but you can look it up in general relativity textbooks. One of the things that you find when you do this is that that orbit will be characterized by 3 different frequencies. And those frequencies are fully determined, of course, by the black hole's mass and spin. Those are the only things it can depend on. And then sort of some, depending on what the orbit geometry is. And so a way to think about it, so this f is just omega over 2 pi. This is being plotted as a function of essentially a measure of the radius of the orbit. As you go to very large radius, all 3 of these frequencies asymptote to Kepler's law. But when we move into the strong field, that sort of Kepler line, so to speak, think about this almost like atomic physics. It's almost like when you put a hydrogen atom in a strong magnetic field and you get Zeeman splitting of the lines. What's happening here is the Kepler line that we're all familiar with from orbits of planets around stars. It describes black hole orbits at large radius. But then when I move into very strong fields, space-time curvature does the equivalent of Zeeman splitting and splits that into 3 separate lines. And what these correspond to, so this tells me about the time, if I imagine an object on an inclined and eccentric orbit, f sub r characterizes the frequency associated with moving from the apoapsis, the largest radius in the orbit, to periapsis, the smallest radius, and back. The theta frequency tells me about the times it takes to oscillate through its polar motion. And the phi frequency then tells me about this thing whirling around the symmetry axis of the black hole. All 3 of these frequencies leave a strong imprint on the gravitational waveform that this generates. What's particularly important, which I want to emphasize, though, is that all 3 of these can only depend on the mass and the spin, fundamentally. Now, this gives us a venue for another precise test of the nature of the space-time that these things live in. So I want to illustrate what I mean by this with an example. So, yes?
By the way, about those frequencies.
Yes.
Omega r, omega theta was first time calculated in the geometry by Gadson and me.
No kidding. Is that right? I will be sure to cite that.
Unfortunately, credit is not well in literature.
Yes.
Time.
Send me the reference. I want to make sure you get cited moving forward. Good. Spasiba. All right. So what I want to do with that, so these frequencies, which our host has so importantly contributed to us, they depend on the mass and the spin. So the Kerr metric only depends on those 2 parameters, but it actually has a shape associated with it, which can actually be characterized by an infinite number of multiple moments. So what do I mean by this? Let me give you an analogy using Newtonian theory. So if I have a gravitating body, we all know about the Kepler, the main Newtonian potential, which Kepler's law arises from. But if the body has some kind of a shape associated with it, there's a correction to this, which depends upon how the mass is distributed through that body. Okay? Things like planets are lumpy. They're not perfectly spherical. And so it's not just this, it's this plus all these corrections due to the shape of the body. By putting a body in orbit around a planet, you can precisely measure the period of the orbit and look at this thing and characterize what its shape actually is. This has been done for the Earth. Okay, and so this is what is called the Grace gravity model. This is sort of, obviously it's been somewhat exaggerated, but the basic idea here is that by having a pair of spacecraft in orbit, very precisely monitoring their relative positions, one can figure out these B coefficients, which determine the shape of the potential, the gravitational potential of the Earth. Those arise, apply Poisson's equation to this thing. You can connect this to the distribution of mass in the Earth. And this is the result. I have to take a moment to talk about what an amazing measurement this is. So GRACE stands for Gravity Recovery and Climate Experiment. So what's not apparent in this little video, let me play this again, is that it's time resolved. And so you can, when you look at this thing, you can actually see the Earth's gravitational potential changing as a function of time due to things like the polar ice melting. during the seasons due to loading of rain in the tropics and in Africa as a function of different seasons. Okay, you can watch the amount of water changing in the Amazon of South America. There was a 26 sigma change in the potential of the Earth right about here on Boxing Day in 2006. That was the earthquake. It was the crust rearranging itself with such fury that it showed up in the gravitational potential from one orbit to the next. It's a really amazing experiment. Nothing to do with gravitational waves, but just cool. Now, it turns out, so we have this sort of infinite family of moments that we use in Newtonian gravity. In general relativity, we also have an infinite family of moments, but they're actually symmetric, so they only depend on one index. And they can only depend on two parameters because of this no-hair theorem. Black holes are completely described by their mass and their spin. So I have a mass multipole moment, and if I have a fluid body, this just describes how masses are distributed. If you go back to that previous little video I showed you, all the lumpiness of the Earth is encoded in these m's. In general relativity, mass flows also gravitate, and so I have a current multipole moment. In a black hole spacetime, if you know the black hole's mass and you know its spin parameter, you know every single one of these things. Now, what this means is that you have a consistency relationship which you must satisfy. When L equals 0, this is saying m sub 0 equals the mass. When L equals 1, it's saying s sub 1 equals the spin angular momentum. When L equals 2, you have something that is totally determined by moments 0 and 1. When L equals 3, you have something that's totally determined by 0 and 1. And so one of the things that people are working on right now is trying to turn these ideas into practical tests that can be applied so that we can understand how it is that we can map these different multiple moments that characterize the Kerr spacetime and use the fact that it shouldn't be too difficult to measure moments 0 and 1 to constrain all the higher ones. You know, some of the estimates suggest we should be able to measure 4 or 5 or 6 of these moments, which would make a very strong test of the Kerr nature of the spacetime. Now, I played for you guys this video last night. Ah, that's loud! Sorry. You know, and I'll go through this quickly. You've already sort of seen this from last night's video, but this is the tool we use to measure all of these different things. And we're in the process right now of, if you go to that the black hole perturbation toolkit, you'll see that we are developing tools for actually making all these various things. So one other thing which I have to mention, which is encoded in this. So you can measure this shape of the space-time. You can measure the masses and the spins with high precision. There's other cool stuff there too. I sort of feel like there used to be these ads on TV in the United States in the 1970s where people would go, but wait, there's more. And they continue trying to sell you some steak knives that you really don't need. I feel like I'm in that mode right now. So when I generated that movie of that small body spiraling into a big black hole, the way I did this was by calculating gravitational waves which radiated off to infinity, and also calculating a flux of gravitational waves that are absorbed by the black hole. And what I essentially did then was impose a balance law. The energy that was lost to infinity, the energy that was lost to the black hole, had to be balanced by the energy that characterizes the orbit. You update from step to step, and that's how you evolve through a sequence of orbits and make that end spiral. Now, this flux to infinity, it's always going to be a number that's positive, okay? When radiation moves far away from the black hole, it travels out to distant observers, impacts our detectors, it's always carrying energy away from the system. But the flux down the horizon is odd. So the sign of this flux down the horizon depends on the relative frequency of the orbits in the hole. So black holes, they're spinning, and you can assign an orbital period, a spin period associated with how rapidly they are spinning. What we find is that if the orbit is moving faster than the black hole's spin, then just like the energy to infinity, there is energy that flows down the event horizon. But if the opposite condition is met, then this radiation that naively looks like it's going down the horizon actually adds energy to the orbit. It's as though there's energy flowing out of the black hole and being absorbed by the orbit. Now that makes no bloody sense at all if you think about what an event horizon is supposed to do. It turns out, though, when we go and look at this, this can be a significant effect. So here's, just to show you some examples. This is from an old paper of mine. So here's an example where I wanted to quantify what the effect of this horizon flux was. So here's a couple example extreme mass ratio N spirals. I looked at a black hole that was spinning very, very slowly. And in this case, it would take about 658 days to spiral in. If I turn off the horizon flux, it took a little bit longer. It takes about a day longer to spiral in. In other words, the horizon flux caused it to spiral in more quickly because it was taking more energy out of the orbit. That makes perfect intuitive sense. But when I made that black hole spin very, very rapidly, what I found is that when I turned the horizon flux on, it actually slows down the N spiral by weeks. Okay, this actually changes. Remember I described to you in the lecture 3 how we can much more accurately measure the phase of these gravitational waves. A 4-week effect is a monstrous effect on the phase. These are tens of thousands of radians that this waveform is being changed by. But it's doing this completely counterintuitive thing where it's like there's energy flowing out of the event horizon. Well, it turns out that what is really going on here is that there is a mathematical duality between the gravitational waveform, the gravitational wave field going into the event horizon and a tidal deformation of the event horizon. And it turns out that the foundations of this were developed by Stephen Hawking and James Hartle in the early 1970s. And there is an amazing similarity between entropy production in fluids and entropy production on an event horizon. So if I have a fluid, then the temperature of the fluid times the rate at which entropy is generated in that fluid is related to the shear of flow lines in the fluid, with a coupling coefficient between them that is set by what's called the shear viscosity of this fluid. Okay, so this is something that has been known about and people have been studying since the 1800s. Now it turns out, if I take this exact formula, I replace the temperature of the fluid with the Hawking temperature of the black hole, and I replace the entropy in the fluid with the entropy of the black hole, which is of course just the surface area of the event horizon. I replace the shear of the fluid lines with shear of what are called the generators of the horizon. Now, the generators of an event horizon are kind of like photons that are trapped exactly on the event horizon. They don't escape to infinity, they don't fall in. They're right on the cusp. It ends up with almost exactly the same formula, with a quantity here that only involves C and G playing the role of a viscosity. So there's this amazing duality between the property of an event horizon and the properties of fluids. And something that rises out of this is it tells me that when I have a body orbiting a black hole, its shape is deformed. And this change to the in-spiral law can be rethought of as the deformation to the black hole tidally coupling back onto the orbit in much the same way that the moon causes the Earth to tidally bulge, and that tidal bulge exerts a torque that causes the moon's orbit to very slowly spiral outward with time. That is probably enough for now. So that wraps up my lectures. The main thing which I want to say, point very much like what Badri made a little earlier today. You guys are privileged, I think, to be able to participate in this field just as it is exploding into beginnings. And I'd urge you to sort of think beyond what can be done with some of these first discoveries. The party is really just getting started. There is a broad spectrum of these things. There are lots of opportunities to get involved. I hope I see you at some meetings in the future. Thank you.
So Professor Scott Hughes finalized, I would say, unfortunately, this very exciting and interesting lecture series at this school. Please ask questions.
Yes.
So my question is a bit related to my previous one.
Yes.
So you said the triangular detector is L-shaped detectors. So considering the total science output, can you compare a triangular detector to two L-shaped detectors that can be put on arbitrary places on Earth? Could you also comment on the total science output per life cycle cost of these?
If I could do that easily, I would probably be a director of a major funding institute. That is very much exactly the kind of thing that people argue about vehemently as they're trying to work out sort of plans moving forward into the future. So people are, even now, I don't know if Nergis is going to talk about this in her lectures or not, but one of the things that, in addition to plans for the space-based LISA detector, there are plans for future ground-based detectors. Right now, there are two plans that are sort of serious enough that I think something will develop from them on a time frame of several decades. Okay, so probably realistically running close to when I retire. Hopefully not before I die, right? Or hopefully not after I die. One of them is based on essentially a geometry that's very similar to LIGO, but just much bigger. So this is an American plan. Nergis is one of the people who's involved in this because the principal investigator for this plan is a colleague of ours at MIT. And the idea of this thing called Cosmic Explorer is just to sort of, I mean, it does a lot of new technology and it takes the LIGO concept and just pushes it out to much larger scales, much higher powers. You know, one of the major issues with this is that as you're trying to make your arms larger, you got to find a good stretch of ground that you can actually do this on. And so, you know, it turns out that there's some deserts in the western United States that no one's doing much with. And so they're looking into site selection there, things like that. There's another concept which is being developed mostly by the European community called the Einstein telescope, which is actually based on a triangle on the surface of the Earth, actually somewhat below the surface of the Earth. So I mentioned in my, let me pull up my, my previous lecture. Here we go. Yeah, so when I was describing, let's do this one in particular. When I was describing the sensitivity of these detectors, I noted that at the lowest frequencies, you would ultimately be limited by gravitational coupling to ground vibrations. It's an empirical fact that ground vibration, the spectrum of ground vibrations actually gets less as you go underground. Okay, it probably turns around at some point, but there's a tremendous amount of ground vibration that's actually caused by various noise sources on the surface of the Earth that then propagate in a layer that's, you know, several to maybe 10 or so meters deep. And if you can go below that, you are away from those sources of noise. And so one idea for reducing the coupling of ground vibration, the gravitational coupling of ground vibrations, is to go underground. And so the proposal for this Einstein telescope is actually to make an equilateral triangle with 10-kilometer arms, roughly 10 or 20 or so meters underground. So you asked the question, how would one quantify? I'm going to rephrase your question as, could one come up with some kind of a metric to make a science and cost-based decision about which one of these, you know, is the design that you should really go for? And it's such a complicated calculation that, you know, like I said, there are vitriolic arguments about this, and it's really hard to say. One of the advantages of a triangle-based system is that you get independently from a single facility, you independently get the two polarizations of the gravitational waves. So from a science-based perspective, that's a huge plus. But doing the interferometry is a lot harder. If you have right-angled arms, you can use a beam splitter and set things in and set up Fabry-Perot cavities in a fairly simple way. That's just not as easy to do when your arms are at 60 degrees. And so I'm actually not quite sure. Have you looked at all at how they intend to do interferometry in the Einstein telescope? I mean, it's anyhow, many of these designs, the details exist in various reports, but you know, until there's some serious funding to begin thinking about some of this stuff, there's details to be worked out. I think it's perhaps the most diplomatic way of putting it. Yeah.
You understand there's a neutron star magnet merger. You have a very short time. So
Yes.
turn your telescopes for
Right.
the gamma ray.
Indeed.
So, what's the future plan for? I mean, is it enough time to direct telescopes?
So let's talk a little bit. This plot I have up is actually pretty good for this. So remember that so the rate of change of frequency goes as f to the, let's see if I can remember this, I believe it goes as f to the minus 11/3. And so what this means is that at low frequencies, the signal is changing relatively slowly. And so it tends to spend a lot of time at low frequencies, and then it begins to accelerate once it moves up to fairly high frequencies. So right now, so for instance, when the binary neutron star was discovered, the noise curve was not that different from the blue one that I'm showing here. And it basically entered band somewhere around here. And at this point, there was roughly 90 seconds left before it went over to here. Now, in a future detector, it may enter around here. Now, that doesn't look like much, but thanks to this scaling, it will actually take more like probably 10 minutes to spiral across from here. If it is possible, this is a big if it is possible to sort of make a confident detection that you have a signal that is going on during those 10 minutes, you might imagine beginning to think to yourself, could we provide an early alert to look at the direction of this thing when the event is actually happening? Now, you should be cautious about this because even though it spends a lot of time down here in the band, a lot of the power that gives you the resolution to figure out things like sky position and all that comes at the end. Okay, so maybe we can, maybe the gravitational wave detectors will be able to say, a neutron star merger will happen 12 minutes from now. And someone will then say, where? And they'll say, up? Maybe down, right? So, you know, that's the challenge, is actually being able to turn that into, I mean, certainly if you're able to know that an event is about to happen, which probably going to, I mean, this basically happened with the binary neutron star, right? I mean, every person with a big telescope on Earth looked at that event, right? And so if you're able to sort of say, we are 100% confident that an event will happen in 12 minutes, people will begin looking. And so I think, you know, there are gamma ray telescopes in particular, there's quite a few that have large sky capabilities. And so I'm sure that they will then prioritize for those 12 minutes, making sure that there's nothing interrupting so that they can try to detect an event should one happen.
But at what point you're going to understand if it's a neutron star merger?
That's an excellent question, yes. So, well, the thing is, if it is moving slowly across the band like that, you know it is low mass. Okay, and so chances are you'll be able to get a decent estimate relatively quickly of whether it's at least neutron star versus black hole. You know, there's kind of the nightmare scenario of what if nature produces like 1.5 solar mass black holes by some process? Because from the gravitational signal, you could get, there'll be no difference between the two of them. Yeah, but that would be sort of the, that would require a nature who hates us, I think, to do that. Yes?
You mentioned this large black hole, small black hole, and eventually this large black hole started to put energy into the orbit.
Yes.
How could a black hole really emit energy?
So what is going on? This was what the parable of this little video that I showed here is. What's really happening, so mathematically there is a duality. When we initially did these calculations, we're calculating what looks like a flux of energy going onto what is, you know, mathematically it's a particular geometry, it's a particular topological section of the space-time where the horizon exists. But it turns out, and this is what all this stuff by Hawking and Hartle developed, is that you can recast this into an understanding of the geometry of the event horizon. And so what's going on here is it's not that there is anything flowing out to the event horizon, But what's happening is that the event horizon's geometry is developing a bulge. And just as when you have a fluid body like the Earth that has a bulge associated with it, that bulge can exert a torque on nearby orbits. And so what happens in a case like this, so this is one where you can see a rapidly spinning black hole. So what I'm representing here, I should have explained this video a little bit better. So this, okay, ignore the fact that it's green. That represents the geometry of an event horizon. Okay, green represents sort of neutral curvature. That's what it is on its own. It's rapidly spinning, and that makes it sort of centrifugally flattened. And when this body comes around, what happens is it exerts a tide that changes its shape. There is then an exchange of angular momentum between the geometry of the tide and the orbit. It actually slows down the spin of the black hole and spins up the angular momentum of the orbit. It's exactly the same physics as why it is that the moon has the same face towards the Earth. You know, the Earth exerted a bulge on the moon. There was an exchange of angular momentum between the moon's spin period and the Earth's orbit, and right now the moon is spinning down the Earth and causing its orbit to gain angular momentum and spiral actually out away from the Earth. It's the exact same physics, but using general relativity and event horizons rather than fluids.
Topology remains the same.
The topology remains the same.
Angular momentum is not completely lost.
That's right. That's right. That's right.
It's a Hawking theory.
Yes, that's right. That's right. Yeah, it's all, Hawking's theorems all work. In fact, we use them to do the calculations. So,
So, one last question, please. One last question.
Could you show again the angular velocity components? Right?
the frequencies? Yes, yes.
And the problem.
Here we are. Yes. So,
Frequency differs in R, theta, and phi.
right.
In strong field regime.
That's right. In strong field, they asymptotically agree in the weak field
They
regime.
are not exactly periodic in strong field regime. But wouldn't that be a result in precession of orbit? And
Exactly. Yes.
but we should have seen that in gravitational wave form.
Well, it depends on the geometry of the binary, right? So if we see this in the case, so for instance, if let me show very briefly. So I'm just going to put this on for a second and then pause it. Make that little plus thing go away. So unfortunately, the lights are sort of drowning this out. You end up with a very complicated pattern here, which is exactly due to these precessions. So what's happening here is this is due to the fact that the radial frequency does not equal the phi frequency. So that means when it comes in, it sort of does a little bit of extra precession relative to the radial frequency. The theta frequency doesn't equal those as well, and that causes sort of the whole plane of the orbit to precess around. If this thing's orbital plane were aligned with the spin of the big black hole, I wouldn't see any of those effects. I would just see a simple sine wave as this thing came in. Okay, so I have to have an orbital geometry that is sufficiently misaligned and sufficiently eccentric that the precessions that are due to the mismatch of these frequencies can leave an impact. For the cases that we have seen so far, they are consistent with there being no eccentricity. So modulations that are due to the here we go. Modulations that are due to the mismatch of the radial frequency with the others, they're gone because there's no eccentricity. The theta and the phi frequencies, they may actually differ a little bit, but the extent to which they would imprint on the waveform depend on how misaligned the orbit is with the spin of the members of the binary. And even in that case, notice that these don't differ by that much. Okay, they tend to be a little bit closer to one another. The strongest modulations come from this mismatch with f sub r. So Another thing which I personally would be very excited to see within LIGO would be a source with significant eccentricity, because that will lead to some of these interesting precessional effects. Now, because eccentricity tends to be bled away rapidly by gravitational wave emission, that would probably only occur if a binary formed dynamically with parameters such that it very rapidly proceeded to coalescence. Could happen, but it would be rare. We haven't seen something like that yet. Yeah, that's a good question. Yeah.
So you will wear out.
I'm wearing out already.
Everyone may come here.
I will be here for the rest of the week. So yes, yes. What's that?
May they come?
Yeah. I'm going to be here all week. So.
So for the time being, let us thank the speaker once again.